Hello, I'm Dan Prinsinski, the President of Applied Energy. I'd like to introduce Bill Hinton, the Director of Engineering. Bill is going to step us through the demonstration of the Applied Energy product line. Bill, I'll turn it over to you.
Thank you, Dan. The dry voltage stabilizer is simply a physically smaller version of Phaseback. This connects between an adjustable frequency drive and a three-phase motor. This is a variable frequency. It could be any brand of any technology where you try to make a three-phase motor run at any predetermined speed. And to do that, they take three-phase power, they rectify it, convert it to DC, then chop it back up with transistors or IGBTs or possibly some other technology and send it to the drive.
Now, before you turn that on, Bill, again, what if any types of problems will occur between that drive and motor if you don't have this type of protection?
Okay, what does happen, you have high voltage spikes that can be 2 or more times system voltage. That will deteriorate the insulation in the motor windings. You also have a high harmonic content. As we see when we power up here, the adjustable frequency drives will typically generate a high amount of 5th harmonic and 7th harmonic. Harmonics are like octaves in an audio, in a piano or guitar or something. And what they do with the motor, the 3rd harmonic we talked about earlier will try to make a motor stand still. 5th harmonic will try to make it run backwards 5 times faster than it's running forward. 7th harmonic will not only try to make it run forwards 7 times faster than it's running, but it'll try to induce or cause current through the motor shaft. The only way that current can have a path to flow would be through the bearings, causes a little sparking and shortens the life of the motor bearings.
Now, I understand some of the people have actually tried to put ceramics at the end of the shaft of that motor to try to minimize that damage to the bearings. However, that metal of the shaft and that ceramic have actually a different temperature coefficient as far as expansion and contraction. So I don't imagine that really holds up too well, does it?
No, not too well. As we're looking at this particular live shot of the harmonics, we're finding that in this case, this drive is putting out a significant amount of 3rd harmonic, and we'll look at voltage in a bit, but we're putting out a significant amount of 3rd harmonic. I have a disconnect to turn on our small version of Phaseback, calling a dry voltage stabilizer. And we've had an instantaneous reduction from about 45% harmonics down to 10. When you try to reduce harmonics with line reactors or chokes, they operate best when you have a higher amount of current flow. Variable frequency drives put out more noise with the less and less load you have on them. So when you need it the most, they're doing the least for you. Dry voltage stabilizer does not care how much current. It doesn't care where the spikes are coming from. It takes the noise and basically beats it against itself to cancel it. So we've had a significant reduction in harmonics.
Well, geez, Bill, what about waveform distortion between the drive and motor?
I'm going to look at voltage here briefly. We have our 3 phases of voltage, and they will vary all over the place and not be the same as each other. We have 325 volts, 307, and 319, 320. And as we vary this over time, we'll see it does have a significant swing. Voltage imbalance causes heat in a motor. Harmonic distortion causes heat in a motor. Spikes will blow little holes in the insulation, shortening the life of the insulation. What happens as we engage our dry voltage stabilizer, we're reducing the amount of electrical noise significantly, as we saw previously with harmonics, but our voltages are all within about 2 volts of each other. It's balanced, it's going to be more consistent, it's going to run cooler, and cutting the electrical noise feeding a motor by 5% is said to double its life. We have cut it by 85%. So we should at least double and should see significantly more efficient operation because we've reduced all of those harmonic forces that try to stop it, run it backwards, and make it go faster forward.
Now, by stabilizing this waveform distortion that we have there, what effect does that have on the physical insulation between your drive and motor?
The insulation on the wire, the insulation in the motor, and in fact the drive output transistors are all protected because the high voltage spikes, the transient voltage spikes caused by switching transients when the transistors are turned on and off, those switching transients shorten the life of the motor, shorten the life of the wire itself, the cable, shorten the life actually of the devices, the IGBTs or transistor output that is actually making the noise. Now, one benefit of that is because of all the noise between a drive and a motor, most manufacturers tell us that you shouldn't exceed 100 cable foot or have more than 100 foot of wire between a drive and a motor. Now, we have already reduced the noise by not 5%, but 85%. We've already tested well over 1,000 feet of motor power cable between the drive and motor very reliably. So the 100-foot distance because of reflected wave, let's just call it noise, is no longer a problem.
So I guess in recapping, using the drive voltage stabilizer, we're stabilizing the waveforms as far as the voltage is, we're eliminating the transients that occur between the drive and motor, we're reducing the harmonics between the drive and motor. Quite a bit of benefit for one product.
Right, and again, this is simply a smaller version of Phaseback in a new, unique application.
Now to go back and ask one question regarding both of these products we've looked at so far, what kind of life expectancy can we get out of these?
Well, let me talk just for a second about typical surge suppression for a minute. Typical surge suppressors can handle a pretty good voltage spike, but as they see spikes below their clamping voltage over time, it'll actually degrade their metal oxide varistors or their solid state components. That was one of the reasons we decided to have no solid state components whatsoever used in any of our products. They degrade over time. We've decided if that's going to be a problem over time, we want something that will stand up to the test of time, stand up to actual industrial environments and many other environments, including marine and oil fields and so on. But the design of Phaseback is such that none of the components of Phaseback operate outside of their NEMA design characteristics. So they're designed to run 24 hours a day, 7 days a week, 365 days a year for 35 years.
Now that's a calculation mathematically, but now in practical application, you and I both know we've got units that have been in 16 years and counting.
Right. So far, so good.
So far, so good.
Yeah.
I mean, pretty much proving out the calculations that we've run.
Right.
To summarize what you've seen here in this demonstration, every one of these products affects the bottom line of your operation. If you want maximum productivity, maximum profitability, contact us.